A relation, remember, is a connection between two different quantities, and there are different ways that we can represent relations. We're going to quickly review some of the ones you would have been exposed to in the past, and then make sure that we understand the key pieces of graphing, and then we're going to tie that into what specifically is a linear relation. All right, some of the ways we can represent a relation are with ordered pairs, with a table of values, with a graph, an equation, or we can write it out in words. I'm going to start by taking 4 ordered pairs here, and we know each of these represents a coordinate point on a graph, hence the round brackets. That tells us those are specific points. If I put them into a table of values, we know that the first one is always the x value, the second one is always the y value. I took a look at my x values and I decided to list them in numerical order from the lowest to the highest. So when x is -1, the y coordinate that corresponds with that is 4. When x is +1, the y coordinate that corresponds with that is 6. So when x is 1, y is 6, and so on. These then become points that we can plot on a graph. So I know that my x-axis is the horizontal axis. I know that my y-axis is the vertical axis. So when x is -1, we go up, y is 4. When x is +1, we go up 1, 2, 3, 4, 5, 6, and y is 6, etc. And then in terms of the equation, what we're doing is we're taking a look and then we're saying, okay, what are we doing with this x value to get to the y value? And sometimes there's more than one step. In this case, we can see that each time we are adding 5 to get to the y value. And it has to apply to every single value in here. So make sure that it consistently works throughout the whole table. If that's the case, we generally set up all of our functions beginning with y equals. So we're going to say y equals x plus 5. And then this just says whatever x is, we're increasing that amount by 5 to get the y value, which we can then represent in words over here. We have relations that are what we call linear relations, and we have relations that are not linear. In grade 10, we're going to spend a great deal of time dealing with linear relations, and the root word in linear is line. That gives you a hint as to what type of graph we're going to produce when we have a linear relation. Now, it does need to be a straight line. So just think a linear relation forms a straight line when we graph it. If it is not a linear relation, then the graph is going to be anything but a straight line. In my first example here, this is an example of a linear relation because we can see that there's a constant rate of change throughout. Those points form a straight line when graphed. This example on the right is not a linear relation because this dip-de-doo in here means that we're not moving at a constant rate of change. And just so you know, this is what we call a cubic function, which comes up in later years of study. Along with the graph, we can also represent a relation using a table of values or an equation. I want you to take a look at the examples we have here and see if you can identify which ones do you think are linear and which ones would not be linear. If we remember that a linear graph needs to have a constant rate of change, the first table of values we have here on the left-hand side, this is going to be linear. If you take a look at the x values, we can see that as we move along here, we're increasing our x by 1. And same thing on this table of values on the right. As we move along the x-axis, we're increasing the x values by 1. So that is rising by a constant amount. Now you want to check the y-axis. So if I go over here, from 8 to 11, we are adding 3 units. From 11 to 14, we are adding 3 units. From 14 to 17, we are adding 3 units. So that's a constant rate of increase. Whereas on this side, from 8 to 27, we are adding 19 units. From 27 to 64, we are adding 37 units. And from 64 to 125, we are adding 61 units. This is not a constant rate of change. We're not increasing y by the same amount for every one increase in x. That's important. So as x is increasing by a steady amount, this is not increasing by the same amount. That means that this is not going to be a linear relation. Point something out here with this table of values on the left that is a linear relation. This one happens to go up by 1 unit every time, but we could skip a number. Let's say we know the next number should be 6, and then if we add 3 to 17, that would give us 20. So when x is 6, y is 20, that would continue on our straight line. But what if they didn't have 6 and they had 7 as the next value in the chart? Well, 20 plus 3 then gives us 23. This is still going to be a linear relation because I've now gone up by 2 increases in x and I've gone up by 6 increases of y. So that pattern is still a constant rate of change. You can always graph this too. So if we were to just make a rough sketch here, we can see that when we plot those points, they are going to be rising in a straight line, whereas this one again is going to be going up in a line that is not going to be a straight line. Now, there's also 3 equations on this side, and there's 3 equations on this side. I'm going to tell you, we're going to sneak back up here. Linear actually applies to the entire left-hand column, so everything on the left side is linear. Nonlinear applies to everything on the right side, so everything on the right column is not a linear function. So I want you to identify, what do you think makes these linear? And what do you think makes these not linear? So if all you're presented with is an equation, what could you use to identify whether or not it's linear or nonlinear? I want you to pause the video and think about that, and then come back in a second. It was the degree. You're correct. If it's a linear equation, every linear equation has a degree of 1. So remember, the degree comes from the term with the highest degree, and we get the degree of each term by adding the exponents on the variables. So here, this is my only variable. We have a degree of 1. This term has a degree of 1. This term has a degree of 1. So the term for this equation is 1. That's a degree 1. And again, this is degree 1 here, so that makes it a degree 1 equation. On this side, this is the highest exponent on the variable. That means the degree of this equation is degree 2. The degree of this equation is degree 3. There's my highest exponent on the variable. And this is a degree 2. 1 plus 1, when you add them together, that term has a degree of 2. What about if you see y equals 3 over x? That's also not linear. Right now, my variable is in the denominator. If I move it to the numerator, if I reciprocate it, remember that exponent, the sign on that exponent flips. So this here is the same as saying y equals 3 times x to the power of negative 1. So my exponent is positive 1 here. When I move that up to the numerator, the sign on the exponent changes. Negative 1 is not positive 1, so that too is not what we call a linear relation. Okay, so the first thing we want to remember is that if the relation is linear, the graph is going to produce a straight line that indicates we have a constant rate of change. So even if the data is represented in a table of values, you're looking for, does the y increase by the same amount for every however many increases in x? Is that going up continuously by the same amount? And is the equation a degree 1 equation? If it's not degree 1, it's not a linear relation. The thing we're going to take a look at is the difference between data that is discrete and data that is continuous. And the word kind of gives you a clue. Continuous data continues on. When we go to graph it, you're going to identify continuous data if we have a line that connects all data points within here. Discrete data, we're only looking at particular values. We do not connect the line because it's only the values that we happen to be looking at. So something like people, we often use discrete data for because we're not going to have a portion of a person, not usually fractions or decimals in here. Whereas continuous data, I can have something that goes all the way from this point to this point. So something like time, where I'm including every second, every fraction of a second, that would be continuous. The length of your foot would be continuous data because it's going to be growing from whatever your starting point is to whatever your end point is, whereas shoe sizes would be discrete. You can only buy whole numbers or half sizes with shoes. So that's the difference. In terms of a graph, continuous data, you're looking for that straight line. Discrete data is going to be a series of points because we're not including the values in between those points. Last piece that we're going to recall before we take a look at some examples is the difference between an independent and a dependent variable. We do know when it comes to a graph that an independent variable goes on the x-axis. It's the one that you choose first. So you kind of get to say, what are we starting with? And then the y-axis or the y-coordinate or the y variable then depends on that. So for example, we have a function right here. So y equals 2x plus 5. You get to choose what you want to put in for x that will then generate a y value. So I can do anything. Because I'm going to also graph this, I probably don't want to go with -1,000,000 because I'm going to have to draw an awfully large scale. So I don't know, the easiest one, let's put in a negative value, 0, and then 1, 2. I'll just go up by a constant amount. If y, so we're going to take our function y equals 2x plus 5. And you're going to, again, substitute in. If we start with x is -1, we're going to substitute that in. 2 times -1 is -2. -2 plus 5 is +3. So when x is -1, y is +3. Now, that's the process we're going through. And I know in middle school they make you write that out. But we're going to do this mentally now. So we're going to take our next value. We're going to put in a 0. If I put in a 0 for x, 0 times anything is 0. So that whole term is gone. And I'm left with a 5. So when x is 0, y is 5. Continue on. If we substitute in a 1 for the value of x, 2 times 1 is 2. 2 plus 5 is 7. So now y is 7. And the last one, if I substitute in a 2 for x, 2 times 2 is 4. 4 plus 5 is 9. That's going to give me my ordered pairs, which we can then come over and graph. So I know when x is -1, y is 1, 2, 3. So let's put a point there. When x is 0, y is 5. So that is our y-intercept. When x is 1, y is 7. Put a point there. And when x is 2, y is 9. Now, this is not entirely drawn to scale because I drew it myself. But we can see that we have the points that are going to move in a linear fashion. And again, if we go back and take a look here, for every 1 increase in x, y is increasing by 2. Do you connect the dots or do you not connect the dots? Well, in this case, I chose what I wanted for x. Could I have chosen 1/2 or 1/4 or 1/8? Yeah, I could have. So in this case, because this is a function, I can put anything in for x. I am going to connect those dots with a straight line, and then I'm also going to put arrowheads on it to indicate that that can keep going. I could have chosen 1,000,000 for x. I could have chosen -1,000,000 for x. So for any point along this line, it's going to fit into this function. This together in an example. We have a frog named George in our first example, and George can jump a distance of 2 meters in a single leap. If he can maintain this distance on each jump, then we're going to first of all identify, is the relationship between the number of jumps and the total distance going to be linear or nonlinear? Well, if George is going to maintain that distance, so we're assuming he's not going to get tired, and we're also assuming he's not going to be jumping continuously, he's going to be jumping 2 meters every time. So every jump, he's increasing his distance by 2 meters. That's this constant rate of increase, which makes that a linear relationship. When you do a table of values, if you're given a context, we don't just want to put x and y here. You want to identify which is the independent variable and which is the dependent variable. In this case, we know that the distance he goes depends on which jump he happens to be on. So if you want to write in here, this is the x and this is the y. The number of jumps, just kind of think that's what comes first. He jumps, and then we figure out what is the distance that he traveled. I can't choose a negative for this one because a negative jump would indicate he's going backwards. So in this case, I'm going to put down, if George does not jump at all, he hasn't traveled anywhere. If he goes 1 jump, he's traveled 2 meters. If he takes another jump, he's gone 4 meters. If he takes another jump, he's gone 6 meters, and so on. If we go to graph that now, I've already set up my axes, so we know the independent variable goes on the x-axis. In that case, this is the number of jumps. When you create your scale, it doesn't matter what numbers you put, but make sure that they are evenly spaced. This is 0 at the origin, so I'm going up by 1, up by 1, up by 1. And again, because he's not going super far, I continue to go with a scale of 1 on the distance, and I put my units in brackets here. So George doesn't jump, he travels nowhere. He goes 1 jump, he travels 2 meters. He goes 2 jumps, he travels 4 meters. And again, that's kind of a rough estimate. He goes 3 jumps and he travels 6 meters. You can see that's going to be linear. Now, should we connect the dots? In this case, no, because it doesn't give us any information about George taking a partial jump. So I'm going to leave those just as discrete data. And I am not going to connect the dots there. Last thing, because they do give you a context in this case, it's not just a function y equals something x. We want to put a title so that people who look at our graph know what it represents. So any title that represents that scenario. In our next example, we have 3 different scenarios, and we're going to identify whether or not they're linear or not and give a reason for our choice. I want you to pause the video and try these 3 examples and then come back and see what you think. Okay, so in my first example, we are renting a dance hall, and we're spending $200 for the hall plus $5 for each person who attends. So our flat rate is going to be $200. We're charging $5 for each person. So on top of that $200, if one person goes, we're going to pay another $5. If 2 people go, we're going to pay another $10. If 3 people go, we're going to pay another $15, etc. Because that $5 is going up by a constant rate of change on top of the $200 fee we're paying initially, it is going to be linear, and it's because this is a constant rate of change. So this is linear. In the second one, we're given an equation, and we know we're looking for the degree. 1 indicates it's linear, and we can see because this variable has an exponent of 2 and this variable has an exponent of 2, it is not going to be degree 1. So we can indicate this is not going to be linear because it is not a degree of 1. Incidentally, that's the formula for a circle with a radius of 5. So when we go to graph it, it would not make that straight line. The last example gives us 5 different ordered pairs. Sometimes it helps people if they write them as a table of values. What you're looking for is, does each x increase by the same amount? And we can see that as we go along here, x is increasing by 5. Does each y increase by the same amount? Now, in this case, y is decreasing, but we can see here that we are going down by that 8 every time. So as x is increasing for every 5 unit increase in x, y is decreasing by 8 units. It is a constant rate of change, which means that that last one is also going to be linear because it is the same decrease in y for every increase in x. The last example, we have a relationship between the number of caribou and the number of legs, and we're assuming that each caribou does have 4 legs, as the picture indicates. There's several different ways of modeling that relationship. We have ordered pairs, we have table of values, we've got some graphs, and we also have some equations. I want you to go through and pick out which of those 6 different forms listed would model this particular relationship. So pause the video and then come back. All right, so I know, first of all, that the number of caribou is the independent variable. The number of legs they have depends on how many caribou that we're looking at. So if you go through each of the choices, and maybe let's even start with the graphs. So number of caribou is the independent variable, and the number of legs they have depend on how many caribou we're looking at. If we have, let's say, 10 caribou, 10 times 4 would be 40 legs. If we have 10 caribou, 10 times 4 would be 40 legs. 20 caribou times 4 would be 80 legs. And again, I'm picking some key points on here where I can clearly see what they are. The difference between graphs D and E is that one is discrete and one is continuous. Which should it be? Well, even though I could have 1 caribou, 2 caribous, 3 caribous, in between 0 and 5, which is what this next number would be, I would have 5 dots in there. Those 5 dots are not going to be so congested that I wouldn't be able to see the spacing. So because of that, this is going to be the graph that I want. It's not going to be this one here because we're assuming we have half of a caribou or a portion of a caribou. So I know that this will represent the data, this will not. In terms of the equations, A and C are my 2 choices. We are multiplying the number of caribou by 4 legs. We are not adding them on every time. If we were, let's say we have 2 caribou, 2 plus 4 is 6 legs, and I know that 2 caribou should have 8 legs, so I know that's not the one that I want. Take a look at the ordered pairs. No caribou, no legs. 3 caribou, 12 legs. 3 times 4 is 12, so that works. 8 times 4 is 32, 15 times 4 is 60, and 50 times 4 is 200. You have to check every pair, and because they all work, that also is what we could use to model that relationship. And again, that's discrete data. We have a series of ordered pairs. And then in the table of values, if you go back to the original equation, which we already established, we know that we're multiplying the number of caribou we have by 4. So that's what you want to check for. 3 times 4 is not going to give me 6. 6 times 4 is not going to give me 12. So this is a table of values, but it's not one that models this relationship. So that is not going to be a choice that we pick. So that just gives you some indication, and a lot of it is review, but it kind of starts to tie together. What are some of those basic components when it comes to graphing? And then we're going to utilize those pieces to start to build on this.